So good morning, everyone. Thank you very much for attending this webinar and for the opportunity to talk about some of this work. Um, this what I'm going to talk about is really motivated by the idea that policies are being implemented in across the world and in a number of cities across the United States to induce a shift to electric heating. And the question I'm going to try and answer over the next 15 or 20 minutes is whether that first reduces energy use, whether it reduces environmental impact, and how it affects consumers' energy bills. So I probably don't need to say very much about this slide. If you're trying to achieve electrification of space heating, heat pumps are an efficient way to do this. What I ought to say at this point is that most of what all of what you're about to see refers to air source heat pumps and not ground source heat pumps. So this analysis assumes air source heat pumps. We've run the analysis for close to 900 different locations across the United States. They've been run for what is a typical home in that location in terms of its size and insulation and so on. The analysis also assumes makes different assumptions about what the existing heating fuel is in those locations. So as you can see, in most of the country, the existing heating fuel is assumed to be a natural gas furnace. And in the analysis, I assume that it's a fairly efficient natural gas furnace, a 90% efficient furnace. The exception is that in parts of the southern United States, I've assumed that the existing heating fuel is resistive electric because, in fact, it is more common in that part of the country to use resistive heating. So I'll dive quickly into the results, and I can explain how we got to these numbers in the Q&A and in offline discussions if you like. But what this chart shows you is the following. Each circle is a typical family home in a different location in the United States, or each dot on this graph is a different location. The locations are color-coded based on the nature of the electricity grid in that location. So all the yellow circles are in California. All the green circles here are an electricity grid region called RFC, where Ann Arbor is, for example. These beige circles are sort of the Northeast, and so on. And the shape over here tells you what the current fuel is. All the circles are natural gas, and all the triangles are resistive heating. So as you can see, resistive heating is assumed to be much more prevalent in the South, in Florida, and in Texas. On the x-axis, this tells you what the benefit is for a household that shifts from natural gas to an air source heat pumps. In terms of dollars per year per household. So this is the monetized benefit from reduced carbon dioxide emissions. And on the y-axis, you have the monetized benefit from reduced criteria pollutant emissions. Now, a negative number means that switching to heat pumps with the current electricity grid actually increases the amount of damage. And the red line that you see here is drawn so that any point that is above this line is such that the sum of both those damages is positive, and any point that's below this line is such that the sum from both those damages is negative. So if you're above this point, switching to heat pumps reduces environmental damages, and if you're below this point, switching to heat pumps increases environmental damages. So what you see here is that if you're currently using resistive heating, it's a no-brainer. Switching to heat pumps actually reduces environmental damages. But apart from a few places in California with the current electricity grid and with the current housing stock, importantly, it's hard to find a location where a switch to heat pumps produces an environmental benefit. Now, this is true for a typical home. Towards the end of the talk, I'll modify that statement to account for the fact that there's a diversity in the housing stock. But this is what we found for a typical home.
And maybe you're going to get to this part, so let me know if you are. But the question I have is more of that's like that snapshot in time of the damage if you make that transition now. But do you consider the future of where the grid is headed in this?
Not here, but I can talk about that in maybe 10 minutes.
Okay, great.
That can be the last thing that I talk about. So so what you see is that both is that in some places you have a CO2 benefit, but the criteria pollutant damages are large enough to sort of overwhelm that benefit. This is because you produce electricity in a gas turbine, you're burning it at a much higher temperature, and you're burning compressed air, and the NOx emissions from a gas turbine from electricity generation are larger than just burning gas in your furnace. That's really what this boils down to. What is also interesting from the point of view of someone trying to design policy is that there are a number of places where a switch to heat pumps with current electricity prices would actually save you money. There are places in California, there are places here in the sort of mid-Atlantic and East Coast where you would save money from switching to a heat pump, but you would actually increase environmental damages. So you're on this side of the you're in this quadrant basically. Over here, you're reducing costs but increasing damages. Sorry.
Part, there was a question. Did you use average emissions of the generation mix or the marginal non-baseload emissions?
These are the marginal non-baseload emissions.
Thank you.
For the current electricity grid. Thanks for the question. Now, as I said, those results were for the average housing stock. The news is much better once you account for the diversity in the housing stock. So this is the same map that you saw. This is the analysis for a number of cities that are in the south, the CERC region of the electricity grid, and an RFC. And what you see is that for if you run this analysis for a representative sample of the housing stock, you end up with houses where you already have heat pumps, houses where heat pumps actually save money, houses where heat pumps save money but produce public damages, houses where heat pumps produce actually increase people's energy bills but produce a public benefit, and then you have houses where the heat pumps produce a net disbenefit to society. That is this part here, where the sum of the private benefit and the public benefit is negative, and then you have this hat space where the public benefit is negative. So the hat spaces are all places where you have where you increase pollution by switching to heat pumps, and the other colors are places where there may be a public benefit but there's a private loss. And what you see here is that in most cities in both of these regions, you could actually justify a much larger penetration of heat pumps based on the total benefits. These light blue areas here are where people don't save money, but the public benefit is large enough that policymakers should subsidize them to adopt heat pumps. And so what we see here is that it's socially optimal for there to be a much wider heat pump penetration than there currently is, once you take into account the diversity of the housing stock. And this is the same analysis repeated for other regions. So this is a region called the Southwest Power Pool, which is sort of this south of the Midwest. This is in Texas, and this is in the West Coast. So in the West Coast and in Texas, you have an interesting situation. Texas is a fairly coal-rich electricity generation mix. So you have a situation where the optimal heat pump penetration is lower than in other parts of the country. And in the West Coast, again, it's a bit mixed. You have places in the Pacific Northwest where electricity is extremely cheap and extremely clean because it's basically hydro. And you have other places where electricity is really expensive. And so you don't, a very large heat pump penetration is not optimal. So the WEC, as befits such a large region, is obviously much more mixed.
What
Sure.
degree does, and maybe you're going to answer this later, cooling come into play? Because I suspect this is focused on heating only, or is this both?
So this analysis accounts for the fact that heat pumps are likely to be more efficient air conditioners also. So we assume a fairly efficient heat pump, and then for each of the houses that we simulate in this range, we use an air conditioner of representative efficiency. So if it turns out that 30% of the houses in Dallas have air conditioners with a SEER rating of, I don't know, 11 or something like that, then 30% of the houses that we represent have a SEER rating of 11, and so on. Does that make sense?
Just so if I can summarize that this is accounting for heating and cooling and not just focused on heating. Great.
Correct. This and will yeah. And finally, this is the same analysis again for the Northeast, for Florida, and for the Upper Midwest. Again, in the Upper Midwest, you have extremely cold weather. In Florida, you already have quite a lot of electric heating and heat pump penetration. And in the Northwest, again, in a number of places, you have fairly clean electricity. But that's offset by the fact that you have very cold weather. So it's a bit of a mixed bag in the Northeast. And Brett, I think this maybe speaks fairly directly to your question, which is what happens if you assume that the heat pumps get more efficient. This accounts for both air conditioning and heating. And our baseline is here. We're assuming a seasonal efficiency rating of around 14 and an HSPF of 8.5. And as you increase that efficiency, your penetration increases, but you need to substantially reduce the cost of installation for it to be economical for people based on their private calculation alone to install heat pumps. So what this does not assume is any kind of policy interventions. If there was a carbon tax, if there was a rebate for installing heat pumps, this analysis would change. But based on the merits itself, you need to have efficient heat pumps and cheaper heat pumps to get to above 60%.
You bring up and I wasn't referring to the heat pump getting more efficient, but I'm glad you did bring that up. And then you said cost. Now, when you're saying cost, are you just saying all things being equal, somebody's paying out of pocket for a heat pump system in comparison to a new gas furnace and air conditioner?
Yeah, so I think this analysis makes that assumption. We are doing a bunch of analyses where we're running sensitivities where, what happens if you want to replace your air conditioner and replace it instead with a heat pump, which also gets rid of your furnace, or if you're replacing only your furnace and you replace it with a heat pump, which also means you prematurely retire uh, your air conditioner.
Okay. So yeah, so back to what I originally was saying, and I'm seeing a lot of comments coming in, pretty much, I think, speaking to this in different ways. And maybe you're going to get to it, but we were talking more about the actual grid cleaning up and/or prices coming down over time. So all these states and communities are making these zero carbon goals. States have, somebody mentioned states have renewable portfolio standards. So that's what we were saying, like the grid getting clean over time. If you were going to address that or not?
I will.
Okay.
We will. I'll get to it in just a second. The other thing that is important here is the effect of switching to heat pumps on the grid. So if you switch to heat pumps and you measure the household hourly peak demand and look at what the change is, you end up in a situation where you increase peak demand pretty substantially in the parts where the current mode of heating is natural gas. So of course, you reduce peak demand in places where you're currently using electric heating, but you increase it in places where you use natural gas. This assumes that you have a dual fuel solution, and this accounts in a lot of these places, you shift from a summer peak to a winter peak. So this is not like your winter peak goes up, but the overall peak is still determined by a summer peak. This just increases annual hourly peak demand. And so this is something that the electricity grid has to prepare for. And if you just had resistive electric backup, so where the heat pump basically didn't have a dual fuel option, then the increase in peak demand is really very substantial. And this is fine when heat pump penetration is low, but this is something that grid planners have to account for, and that we have to design a housing stock for, frankly, for when heat pump penetration increases. This again assumes our current fairly leaky housing stock, but it can be made better, of course, with weatherization. So, Brett, I'll just jump to what happens as the electricity grid gets cleaner. And I looked at a scenario that EPRI has called the transformation scenario. And this is the most aggressive scenario that EPRI has for reducing, for cleaning up the grid. So it assumes that on average, you reduce the CO2 emissions intensity, and I assume that you reduce the intensity of other emissions by 9% per year. In practice, we've managed to clean up the grid by 2 or 3% per year. So this is very, very aggressive. This assumes that between 2015 and 2040, or between 2015 and 2020, you get about a 40% reduction in emission intensity. And in fact, we're through 2020 now, and the actual reduction in intensity has been 10 or 15%. So this really is a scenario where we get our act together, and EPRI assumes a very steep carbon tax in order to do this. So this picture tells you what would happen to the environmental benefits and costs of installing a heat pump if we manage to clean the grid up that rapidly over the lifetime of the heat pump, assuming that the heat pump was installed in one of these years. So this is the lifetime benefit from reduced criteria pollutants. This is the lifetime benefit from reduced CO2 emissions. And if you install a heat pump in 2020, which is the year of installation here, you can see that in large parts of the country, if you did clean up the grid that rapidly, the heat pump would actually produce a net environmental benefit. but in parts of the upper Midwest and in the Mid-Atlantic and East Coast, that would still not be true because the power generation mix is still too dominated by coal. And here I'm going to show you what happens as you clean up the electricity grid. So by the time you get to 2024, 2025, you get to a situation where across the country you're producing a fairly large environmental benefit overall. Brett, yeah.
What this is great. This is a great chart. Thank you for sharing that. What you know, how did you factor in or maybe not factor in the idea that if people start adding either solar directly to their homes or using community solar where they can sort of indirectly retain those renewable energy credits, and of course then offsetting, you know, because we can't, you know, we can't offset gas with solar. There's no way. It doesn't bring the burnt carbon back down, you know, no matter how many solar panels we have. So in what ways did you factor that in at all, or consider that site solar, or in some rare instances wind or water, I guess, within what you were thinking, or not?
I have not. So this analysis assumes that your marginal source is always the electricity grid. And EPRI scenario basically achieves decarbonization by shifting to gas plus CCS. So the assumption underpinning the scenario is that load following electricity is provided by gas plus CCS. And that mean you're right, that may not be a very good assumption. And if people did put solar panels on their roof, this would change. But this also shows that if you do want to accelerate the shift to heat pumps without cleaning up the grid this rapidly, then you can't have the shift to heat pumps alone. You also have to do solar.
Right. Yeah. So you're saying just focusing on, well, and I guess, and we were talking about this before the call, right? And what role does energy efficiency being assumptions as far as the shell play in any of the research you did?
Well, so let me actually, yeah, we can go back to this series of charts. So one of the dimensions on which the different houses that we simulated here is energy efficiency and the size of the house and so on. And so this analysis makes it clear that there are houses out there which are either small enough or efficient enough, or which currently have gas furnaces that are inefficient enough that a switch to heat pumps makes sense. But what this does argue for is a targeted approach. So, for example, in Amarillo, Texas, any of these places would benefit from shifting to heat pumps, whereas only this proportion of houses actually has heat pumps. And this analysis accounts for the fact that different houses have different levels of efficiency. And if you, Brett, I suspect your question was what happens if, along with a heat pump installation, you improve the efficiency of a house? What are the economics of doing that?
Yeah.
I haven't done that analysis yet. But if you assume the existing housing stock, this tells you something about what the economics are.
Sure. Have you, in your study, considered, from an emissions standpoint, what we're starting to learn is that you know, natural gas running through pipes all over the place is leaking all over and putting them, you know, directly into the atmosphere. Was that made in your assumption at all, accounting for that? I mean, because electric always gets dinged for line loss. You hear it all the time. Can't go electric because of all the line loss, but nobody talks about all the gas loss that's leaking everywhere and potentially polluting communities.
Yes. So in this analysis, we've actually accounted for some leakage of natural gas. I think we've assumed like a 0.5 or 1% leakage or something of natural gas. And of course, in terms of the greenhouse gas damages it does, that's extremely potent. The problem is that on the other side of the equation, a lot of electricity right now is also generated using natural gas, and there's some leakage in that network also. Even though the transmission network is probably, for natural gas, the transmission network is probably a lot tighter than the distribution network, and so on. So the short answer is that yes, this analysis accounts for methane leakage, which is very potent.
Great, great. Well, I do want to give your colleague Lucy some time to talk about the other considerations we have to make when we're looking at heat pumps. Do you have anything final to say before we can hand it to her?
No. I'm done. And so, yeah, over to Lucy to talk about the more interesting question of how this all affects house prices.
Great. Thank you so much, Parth. Appreciate it.
Thanks, Brett.
I am handing it off to you now, Lucy. And I did mute out your camera accident. Sorry about that.
Yeah. No worries. Share my camera. And then now I need to share my screen, right?
I think we can see it. You just got to turn on the PowerPoint. So.
Okay, sounds good. All right, great. Thanks everyone for coming. I'm going to talk about the paper that was published this past October, also together with Parth, and also my PhD student Xin Chi and my colleagues Peng Fei and Anand Patwardhan. So this paper was published in Nature Energy, estimating the residential house price premium after the heat pump installation. The Parth already gave some background about the various type of incentives that have existed for incentivizing heat pump adoption. And then also here I want to mention that for our very new president, he also has a plan to through various type of subsidies such as direct cash rebates and low cost financing to electrify home appliances, and the heat pump will play a very important role. But then in academic literature, there is a phenomenon called energy efficiency gap. That is where, despite the fact that there are various types of incentives and the fact that some of these technologies, such as energy efficiency measures, and in some cases heat pumps, even if they do make economic sense, but then diffusion of these technologies is still relatively slow. So this paper tries to tie to the energy efficiency gap phenomenon to show that installing heat pumps does bring positive price premium, which can be a very strong signal to incentivize consumers to install heat pumps. All right, so now directly dive into the data, the main data that we're using for this analysis. We obtained the nationwide residential property data from Zillow.com, which includes more than 150 million homes in 51 states. And there are two main parts of the data. The first one is the assessment data, which include for each individual homes in the US, it includes the property characteristics, such as the number of stories, number of bathroom, and also its energy technology attributes, such as whether it installed heat pumps or not, whether it has solar panels and other type of energy-related technology. It also has the property address for each individual home, so that we can do some matching of the address. And then, so very importantly here, you can see that for the assessment, we have the data from since 2016. And since March 2016, the assessment has been done almost twice per year, which form a very nice panel data set. And then the key, the nice thing about the panel data set is that we can infer the time window for each home during which the heat pump was installed or not. For example, let's say we have one home when the assessment was done in March 2016, that home didn't adopt heat pump. And then in the next assessment data conducted in February 2017, And then if that home did have heat pump, and then we can infer that the heat pump was installed for that home during this time window between March 2016 and February 2017. And then once we know the time window, and then if that home was sold both before March 2016 and also after February 2017, then we know that the sales after 2017 will be the sales after the home or installed the heat pump. And then the sale before 2016 will be when the home did not have any heat pump. So that we have the difference of the transaction prices that can show us what could be the additional value that's brought by the installation of heat pumps. So basically we have for each homes that type of information so that we can infer the pre-installation and the post-installation transaction prices. And that brings to the second part of the data, that is the transaction data. And then for each of the home in the Zillow data, we did get the information of all the historical transactions since early 1900s. All right. Okay, so here, based on the latest assessment data, is actually, so we updated this graph is based on the latest assessment data in 2020. This graph shows you at the county level what's the density of heat pump adoption, which is the number per 10,000 persons. Now here you can see that the most adoption happened in the Washington state as well as in the southwest part of the region, which imply that basically these regions have relatively mild winters. That could be a factor where people, when they adopt heat pump, they might run fewer problems if there are very cold weather. So that could be a factor showing the heterogeneity of such different density of adoption. All right, so now quickly about our method. If you have any question, you can ask me later, but I will just quickly talk about the method here. So basically, we're doing a difference in difference analysis. For the heat pump home, we do have the control home, which are the home that do not install any heat pumps. And then we have for both the control house and the treated house, they were sold at least twice in our study period. And for the control house, for example, when it was sold in the first time period, it was sold at lower price, and then when it was sold at the second time period, it was sold at a higher price. And then we have the difference of the prices for the control house. And then for the treated house, which is the house that did install the heat pump during between time 1 and time 2, we also get a difference of the transaction price for that heat pump house. And then we subtract the difference of the transaction prices of the control home from the difference of the transaction prices of the heat pump home. And then that difference in difference is our estimate of the treatment effect on the housing price premium that's induced by the heat pump installation. So the key idea of this method is to control for any confounding factors that could also influence housing values, such as building characteristics, building conditions, and so on. All right, so basically, as I mentioned earlier, we have the treated home. Those are the homes that installed the heat pump between 2016 and 2018. Then we also have the control homes that did not install any heat pump and keep using one specific heating system all the time, and also were sold at least twice during the similar time window compared to the treated group. And in order to do the difference in difference analysis, the heat pump home had to be sold at least twice, once before the heat pump installation and once after the heat pump installation. And then that will make our sample sizes smaller compared to the sample size where the heat pump installed, where the homes install the heat pump but since the installation were not sold. For those type of homes, those were not included in our analysis because we cannot do the difference in difference analysis. Okay, so in the end, in our main difference in difference analysis, we have about 14,000 houses across 23 states. And then these 14,000 houses are in the treatment homes, meaning that these are the homes that install the heat pump. And we also have about 440,000 houses in the control group. And then when we select the control group, we do have a matching criteria. We basically we match the treat homes and the control homes that are in the same county. Okay, so they have to be in the same region so that we know that we're comparing houses that are in the same housing market. And also, the key confounding factor that can influence the estimation of price premium that's induced by heat pump installation is that the concern about other type of housing upgrades or energy technology installation that could be happened around the same time of heat pump installation. And to rule out that concern, we remove the houses that were remodeled after 2000 so that we can, any price premium that we estimated will not be due to any house remodeling. Okay. All right, so I'll skip this slide. So this is our econometric model that we're using to estimate the housing price premium. And then,
real quick question, Lucy, was there any other aspects of the home that was looked at as far as upgrades, insulation, air sealing, energy efficiency wise?
Yeah, so that's a great question, and I will actually talk about this in just a few slides. And so the short answer, yes. So we did it in several ways, which I will show you, and that gave us a lower bound of the price premium. Yes. So, and also this is another test to help us ensure that before the heat pump homes, before they adopt the heat pumps, we did compare the difference of the transaction prices between the treated house and the control house. And then these are in the pre-installation time period. And then here, these black dots shows the difference of the transaction prices, and then the vertical line shows the 95% confidence interval. So basically, the key idea from this graph is that before the heat pump installation, the difference of the transaction prices between the heat pump home and the control homes are not statistically significantly different, which ensure that we're indeed comparing apples to apples, meaning that we're not comparing two different houses so that the house premium can be due to other factors. So this graph helps us ensure that the control homes and heat pump homes were similar prior to heat pump installation. All right, so I think this is related to the question that Brett just mentioned. We did look at these other housing attributes, such as number of stories, total bathroom, bedroom, total rooms, building condition, and building quality. We look at whether the heat pump homes and control homes in the pre-installation period, whether they differ significantly in terms of these basic building attributes. And we find that they were almost similar in all the attributes except for total bathroom. So, and also except for building quality. And then this basically shows that we need to use more sophisticated econometric methods in order to rule out these other building characteristics impact. Right.
So there was a question, and I wanted to make sure I heard you right, but you're saying that the idea of upgrading HVAC in general, were you able to evaluate that as part of this, or you're saying you need more robust techniques to do that?
We need more. So we are isolating these other potential upgrades. So in other words, we're isolating the impact from heat pump from any other potential building upgrades, which could also include, for example, upgrading the air conditioning system separately, or upgrading insulation or window treatment.
Okay, so the idea that just in general, when you upgrade something, it increases value just inherently, potentially, that's been accounted for.
Correct, yes.
Oh, thank you.
Mm-hmm. Mm-hmm. All right, so here, this is also related to the question that we just discussed. We did also control for, we tease out the confounding factor from a very comprehensive set of building features. These are basic features that I already mentioned, and then there are also more nuanced building features such as building condition and building quality. And then we all controlled for these in our analysis, so that we're not saying that the 17,000 price premium is also a factor of these other building condition or building quality. All right, so now here comes our basic results. I know that this is a slightly complicated table, but then you need to only focus on this first row here. That is the percentage increase in transaction prices if a home installed a heat pump. And then here, these different columns shows the different models where we include different econometric techniques, such as different fixed effects to control for various type of confounding factor. And then the model that we prefer is the last model, that control for more confounding factors. That gave us price premium of 7% and on average about $17,000. And then, as I will discuss in just a few slides, this econometrically directly estimated price premium will be the upper bound because there could still be any concern about contemporaneous energy efficiency upgrades or building condition upgrades that are not yet being controlled for in our baseline model. So next, I'm going to talk about how we control for those other energy efficiency retrofits or building upgrades that could be done around the same time of heat pump installation. So our first step is to look at contemporaneous energy efficiency retrofits. What we did is that we used the publicly available residential energy consumption survey from EIA to look at the correlation of heat pump adoption with the adoption of this other energy efficient retrofits, such as Energy Star qualified windows, Energy Star qualified water heating, energy efficient light bulbs, refrigerator, clothes dryer, dishwasher, clothes washer, solar panel, solar water heating. Now here these blue bars shows the marginal increase probability of adopting energy efficiency measures of a heat pump home compared to a non-heat pump home. And these blue bars are all positive, and some of them are statistically significant, meaning that it is indeed true that for a heat pump home, it is also more likely to have these other energy efficiency retrofits. So, and then what we did is that we web scrape the value of these other energy efficient retrofits from Home Depot, and then multiply each value by the marginal increase probability and adding them together, and then subtract that additional value from our estimated upper bound in order to get a lower bound of the price premium. So in other words, we're subtracting the values of these other energy efficiency retrofits in order to get the additional value that's purely induced by heat pump installation. All right, and also we get rid of confounding factor from building retrofits as well. Here we use the Zillow data to basically do a hedonic regression where we regress the transaction price on these other building attributes, such as probability of changing roof color, building quality, building condition, number of bedroom, bedroom, total rooms, and number of stories. Now here you can see, and then we get the value of each of these retrofit property. And then we also regress heat pump. We also look at how heat pump adoption is correlated with each of these building upgrades. Now again, these correlation as shown in the blue bar are positive, meaning that it is indeed true that a home that has installed heat pump are also more likely to upgrade their roof cover to have higher building quality, higher building condition, larger rooms, higher number of rooms, and then a larger number of stories. So again, we use the value that estimated from the hedonic regression multiply by the additional probability of doing this building upgrades and adding them together and subtract from the upper bound that we estimated. And then we obtained a lower bound of the price premium, which is about $10,400.
So you said people who typically add heat pumps tend to increase the size of their home, correct?
That is here we're not showing the square feet, but then they can be more likely to have, for example, add another room or add another bedroom.
Oh, like maybe shrink a room to add another bedroom then.
Yes.
Would that be?
Yeah.
Oh, interesting. Okay. Yeah. And sorry, same with energy efficiency, other energy efficiency measures?
Correct. So they're more likely to adopt these other energy efficiency measures as well.
Thank you.
Mm-hmm. Oh, great. And then next we also show how these price premium are correlated with other factors. And then here, the first graph shows how the price premium change with respect to environmental awareness. Here, x-axis shows shows the degree of environmental awareness. The larger number means the people are more environmental awareness compared to the lower value. And then here you can see that for people that are not very environmental driven, it is natural that they might have they might assign lower value to heat pump homes. And then for people that are in the middle of the environmental awareness spectrum, they are actually assigned the highest value to heat pump homes. But very counterintuitively, for people that are very environmentally consciousness, they actually will assign relatively lower value compared to people that fall in the middle. So our explanation is that for these people that are very environmental driven, they might actually know more about heat pumps. And as Parth mentioned, in some regions, heat pumps actually generate negative environmental impacts. So it is likely that these people, when they know more about heat pumps, and then especially if they fall into the regions where heat pumps can generate more carbon or environmental damage, then they will assign lower value. And then we'll also look at how the price premium change with respect to heat pump density. And then here you can see in panel B of the figure, when the heat pump density is very low in the region, then it is likely that the market is not mature yet in that region, so that the cost, for example, the distribution cost or installation cost will be higher in those regions compared to when the heat pump market is relatively mature and fall in the middle. However, when the heat pump density is very high, the premium is also falling. That could be due to economies of scale or learning by doing. When a lot of contractors, they have already gaining a lot of experiences installing heat pumps, then the cost of installation will be also low. So that the inherent value of heat pump system will also be falling, so that the price premium will also be falling. And then we'll also look at how weather influence the price premium, and this is also intuitive. Heating degree day and cooling degree days, the premium will be highest. Here, for example, when the cooling degree day falls in the middle. And then we'll also look at how price premium change with respect to personal income. And here, intuitively, when the income is low, then people will assign lower value to heat pumps. It could be because about the affordability. But then here, when people have a much higher income, for these very high income households, they also assign a lower value compared to households that have income in the middle. And this could be due to the fact that these households, when they have much higher income, then they might prefer the technology that are more savvy, energy efficient savvy, so that they can show their environmental status, or that they can showcase, for example, they have solar panels or EVs. Those are more likely to attract attention compared to installing heat pumps. All right, and then lastly, we compare the price premium, the lower bound and upper bound, with the net benefit, as well as the cost of installing air source heat pump. And we do this analysis for the two regions where the heat pump density is the highest. And in both regions, we can see that the price premium is higher than the cost of installing air source heat pump. So, and then the reason could be because of the transaction cost of installing air source heat pump. So so if the consumer, for example, if there's no transaction cost, and then if they know this information, for example, if they know that they can resell the heat pump home with a price premium of $8,644, versus if they only install the heat pump themselves, it will only cost him $8,000. Then he will, of course, not buying a home with a heat pump, but instead buying a home without heat pump and install the heat pump himself, and then sell the home at a higher price so that he can gain a net benefit from this. So in the equilibrium market, that will not happen. So then we need to explain why there's a difference between the price premium and the cost of installing heat pump. And then our explanation is the transaction cost. For example, there's the cost of searching for the adequate contractors. There's a cost of comparing, actually knowing the technology, the cognitive costs, which all take time. There's also the cost of, for example, waiting in the home for a few days or even for weeks to get the system done. And all those add up together could be worth about $600. And that's the transaction cost that will actually cause a household to buy a home with already have heat pump installed, instead of buying a home without heat pump, but taking all the costs to install the heat pump themselves. All right, so lastly, to summarize, our results show that on average, a home with heat pump installed can sell at a higher price, with the price premium between $17,000 and $10,000 compared to similar home without heat pumps. And then the important implication for policymaker, which is tied to the energy efficiency gap that I mentioned earlier, is that they can use such information as a positive incentive in order to incentivize homeowners to adopt heat pumps. Okay, so thanks for your attention, and that's the end of my presentation.
Thank you, Lucy. I know some folks do want to wrap up here before noon, but are you able to stick around for a little bit with us for some of these questions?
Yes, of course.
Okay, great. Well, real quick, for those of you who do want to get going, let me share my screen here real quick. So yeah, if you're looking to get your continuing ed, please do take that survey that pops up. Even if you miss the survey when it pops up when we close out here, it'll get emailed to you an hour later, and then you can take it there. And even if you don't need CEUs, we do appreciate your time and your feedback, so please take it. For those of you watching this in the future on demand, please take the quiz with an 80% passing rate. You can find the quiz on our website by clicking the YouTube link and then go and dropping down show more under the comments, and then within the comments you will see a direct access to that link. Please take it. And a big thanks to our board of directors, our volunteers, our new executive director, all of our members and our top tier sponsors, Mitsubishi Electric heat pump systems that can take you to net zero for new and existing buildings, single family, multifamily, Rheem air source heat pump systems, Build Equinox, smart ventilation, which is very necessary right now to improve our indoor air quality. Huge thanks to all of them and all of you for joining us. So one question I had for you, Lucy, was to what extent did, and maybe I missed this, appraisers and their official appraisals play a role in these value increases versus just home sale prices?
Yeah, so that's a good question. So we only look at the transaction prices instead of the assessed value, because those are the transaction price are people who actually paying, and then that's their review preference. And then the assessed value can deviate from what home buyers are actually valuing the homes.
Yeah, I can tell in my own personal experience. We added a heat pump, and it was not looked at by any means by the appraiser. It was more of a increased value just for having that versus an old gas furnace, but they were not able to add it, and part of it was just simply because there was lack of comparables in the market. So so that was one thing. So I was looking at the areas that you honed in on, the South Atlantic and the Pacific, where Partha told us that's kind of the biggest areas where we see adoption. What about any general comments on the other areas of the country in regards to what you're finding, or was there just not enough data?
Great question. So we do have 23 states, but then we focus on Pacific and the Southwest. But then for some of the states, we do find that the home value can be negative. But then for those states, we do not show the results here today in the slides because the number of the sample size is relatively small. In some cases, too small. So I'm hesitating to show those results. And then we're more comfortable about the Pacific and Southwest results.
And there was a lot of commentary while you were talking, and we were trying to figure out to what extent you were able to account for brand new gas furnaces and air conditionings in comparison. And it seemed like, from what I could tell, that was accounted for in your control group. But I guess just restating it because there were a lot of comments on that. So
yeah, that's a great question. So our control home can also change into a new HVAC system. So in other words, even though if a house install a heat pump, of course it will be a new system. But then a control home can also have a new system, but that's not heat pump. So our estimated price premium would not be because the heat pump is just new, but it will be just because it's heat pump. And then also we did another analysis where we also look at old heat pump versus a control home, and we also find house premium there. So our estimated price premium, yes, we have it controlled for the newest of the system.
And I know this study focused on air source heat pump systems. To what extent could you make any inferences on ground source, aka geothermal, or could you not make any off of this?
Right now we cannot say that the geothermal heat pump will have a higher or lower price premium because of lack of data. But then given that the house premium that we estimate is higher than the cost, and then of course the cost of geothermal will be higher, so it's likely that the house premium will be higher for geothermal heat pump, but we do not have the data to show that yet.
And then there were some questions about is this all existing, or did you factor in new construction into this?
Great question. These are all existing homes because the homes have to be sold twice for us to do that type of analysis. But then we can do a new. I think we did do a new home analysis in our robustness check in the very long appendix, which you can find on the Nature Energy website. And then we did do an analysis. And it does show some price premium as well.
Great. Well, I want to thank everyone for joining us. I want to thank Lucy and Parth here for taking some time today, especially to go over all this as an important issue as we try to move forward and make our homes and our buildings better. Just real quick, if both of you can state, where people can contact you to find out more, and then I guess if there's anything else you'll be working on in the future, just briefly that we can look forward to. So I'll start with you, Parth. Oh, you're muted. There you go.
So my email address was on the first slide of the handout. There's also a Twitter handle, so I'm happy to chat on either of those forums. What I'm hoping to do next is to try and see how utilities deal with the fact that you would have an increase in peak demand. So if they have time of use charging, if they have concurrent peak pricing, how does that affect people, and how does that affect people based on their income and based on their demographic status? So do poorer people live in homes where that becomes a really acute trade-off, where they're living in leaky homes and now they're being penalized for using electricity when it's cold? Can we expect those people to switch to heat pumps? So I'm interested in the equity question.
Great. Thank you so much, Parth. Hopefully we can have you back with some great study and help get the word out. So I really appreciate you joining us here today. And then Lucy, again, where can people contact you for more information? Anything else you'll be working on in this regards?
Yes, so thanks again, everyone, for joining. You can contact me via email, which I believe is in the last slide of the handout. And you can also just Google my name. It will pop up my webpage, and you can also find the contact information there. And then relate to my future work about heat pump. We do have a study looking at using actual smart meter data to look at how heat pump installation impact the electric grid and the load profile of individual homes. And then also the second idea is to look at also, as Parth mentioned, the equity aspects of electrification. So the idea is that the people who adopt heat pumps are more likely to be those that are higher income, and then because of the premium of that I mentioned. And then when the penetration of heat pump is higher, then that means there will be fewer people using natural gas, and then natural gas companies need to recover their upfront infrastructure investment. They have to increase natural gas price, and then the higher natural gas price burden will be unfortunately be buried by those who do not install heat pumps because they still use natural gas, which will be more likely to be lower income households and underrepresented communities. So we're trying to look at the impact of heat pump installation on natural gas prices and relate to the equity aspect. And then I'd be happy to potential future collaborations.
Yeah, thank you so much for both of you addressing that. It's very important as we make this transition that everybody benefits from it and does not get left behind. That's something that's important to us. We want to keep an eye out on that as well as we talk about these cool technologies. So thank you for focusing in on that, and thank you for joining us, Lucy. Parth, thank you all. And again, just public service commission or service announcement. We do want to see you all in person someday. We love doing online events, but we do want to do in-person events someday. So we need your help. We need you to, stay in when you can, to stay masked everywhere when you go out, and we can use building science to improve our buildings. We need to do that just not because of COVID, but we need to do that in general to make us all healthier. We know we can increase MERV filtration to 13 beyond. We know we can use humidification. We know we can increase ventilation to 62.2 standards, 62.1 in the hallways. And we know that we can beat this thing by using all this above approach. So I hope you will join us, and we will see you next week. Take care, stay well, goodbye.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.